See if that's of any use. Okay, now I figure out how to lift this. Sorry. All right, so we're going to talk about two. Is there no other lights to turn on? So we're going to prove two theorems. Oh, don't worry. My own pins. So we want to prove two theorems. And one of them is called Fermat's little theorem. Not last theorem, but little theorem. Last theorem's harder. And so we'll prove this. And then another theorem we'll prove is called Wilson's theorem. So let's write these down. Ah, good. But that's more visible. Wilson's theorem. Okay, so let me tell you what these are. By the way, if you look in the thing where it says lectures online, I have a bunch of like a Sage worksheet with lots of interacts in code that illustrate playing around with both of these theorems, which you can look at your own leisure. So I'm going to state and prove and explain what each of these are. So first, Fermat's little theorem. This is it's just an observation, but it's kind of a special case of something really general. And it's the following. If you take, okay, so let n be an integer. Let's make it greater than or equal to 1. And I'm going to define something called the Euler Phi Function, Phi of N. This is the Euler. Okay, so I'm proving, I just realized I'm proving a generalization of Fermat's little theorem. Fermat's little theorem is just a special case of the statement I'm about to make when n is prime. So I'll also put, in general, it's called Euler's theorem. Okay, so I'm going to tell you something that happens, but first, let's define a function, phi of n, and this is simply the following. It's the cardinality of the set of integers a, where a is between 1 and n. Let's see. I want to define it for 1, but so I can't do that. Actually, if I put 0 here, it'll work. Okay, and
in the book it says less than or equal to, I think.
Yeah, we can do it at either end, and it comes out to be the same. And the GCD, but you're right. I'll stay consistent with the book. 1 less than or equal to a, less than or equal to n, and the GCD of a and n is equal to 1. Okay, just a number. And you have it for each integer n, each positive integer n. It's just the count of the numbers between 1 and n that are co-prime to n. Okay, so let's just quickly play with it a bit. Phi of 1, phi of 2, phi of 3, phi of 6. What are these? Okay, phi of 1, how many numbers? It's just the cardinality of the set which has one thing in it, namely 1, plus 1. Phi of 2, 1's in there, because 1 is GCD of 1 and 2 is 1. And GCD of 2 and 2, that's not 1. That's 2, so it's not in there. So this is also 1. Phi of 3 is the cardinality of the set of numbers between 1 and 3 that are co-prime 2. So read A is co-prime to n. So here you have 1 and 2. So that's 2. Okay, what about 6? Shout out the numbers that are between 1 and 6 and co-prime to 6. I only heard one person. Still only heard one person. Are they right at least? They say 1 and 5. Those are true. Those are numbers that are co-prime to 6. Are there any others? be really confident that there either are or aren't. Which, are there any other numbers between 1 and 6 and I should get really annoyed because I'm completely wrong. Right? So 2 is not co-prime to 6. So 1 and 5 are the only ones. I hope you're annoyed for a second there. Alright, so now let's do one more. Okay. Okay, what about up to 10? How many are there? What's
1, 3, 7, 9.
Yeah, so you lose the even numbers. So 10 is 2 times 5, so you lose any multiples of 2 and you lose any multiples of 5, but everything else you get. So 1, 3, not 5, 7, and 9. So it's 4 of them. 1, 3, 5, or no, 1, 3, 7, and 9. And that's 4. And there's a lot of really nice things about the Euler Phi function. For example, if you have a product of 2 numbers that are co-prime, phi of n times m, and n and m are co-prime, then phi of nm is equal to phi of n times phi of m. That's something we'll prove next week. So there's lots of nice things that take some real work to prove, but make it a lot easier to understand and compute with this. This is only true, it's false actually in general, but it's true if the GCD of n and m is equal to 1. Then you have that. Okay, yes?
Is there a simple equation that describes what phi of n is? Is there a simple equation that describes what that
Yeah.
function is?
So, I don't know what you mean by that, but
Elementary.
if you want to compute phi quickly, you can, well, the best you can do is you have to factor the number into a product of prime powers, and then for a prime power, there's a simple formula. Phi of p to the k is p to the k minus p to the k minus 1. So that's pretty easy. For example, phi of a prime is just that prime minus 1. And the way you get this is you just look at the numbers from 1 up to p to the k, and you have to throw away all the multiples of p, and they're exactly p to the k minus 1 multiples of p in there. Because it's p to the k divided by p of them are multiples of p. And then you use this, and so what you end up with is a formula that says that phi of the product, say I equals 1 to r of p sub I to the e sub I is equal to the product pi to the ei minus pi to the ei minus 1 over all I equals 1 to r. So that's a formula for phi of the number. It's, in order to compute this, you have to factor your number as a product of prime powers, and there's no easier way of computing phi, as far as we know. If you could compute Euler Phi of a random 100-digit number, then you could break the RSA public key crypto system. A fact we will prove in a week or 2. Okay, when we get to public key cryptography. So phi is hard to compute. So let me tell you what Fermat's little theorem is. It's another fact about the Euler Phi function, which I haven't stated yet, but it's just some information about it. So here it is. Theorem. If, let's see, A is co-prime to n, then A raised to the power of phi of n is equal to 1 modulo, it's congruent to 1 modulo n. Okay? So this is a hopefully not obvious statement about the Euler Phi function. But let's just try an example. So phi of 10 is 4. So what this says is that if I take any number that's co-prime to 10 and raise it to the power of 4, I'm supposed to get 1 modulo 10. So it's a fact forevermore. So, and this statement right here is incredibly important and useful for, I don't know, most of public key cryptography. If you don't understand this, then you don't know what's going on. So let's just take anything like 3. 3 to the power of 4 better be congruent to 1 mod 10. Without even doing any further work, you know that the last digit of 81 is 1. That's what that says. 3 to the power of 4 is 9 squared. 9 squared is 81. And when you reduce the number mod 10, you're getting the last digit. So if you take any number to the power of 4, if that number is coprime to 10, if it's not divisible by 2 or 5, you'll automatically have the last digit as 1. That's a way to think about this. But of course, it's much more general. So now let me give you 2 reasons why this is true. First, I'll just tell you how it's an immediate corollary of a very basic fact in group theory, but you maybe don't know anything about group theory, or you want to see why this is true without using group theory. Then I'll give a proof that doesn't use any group theory at all, just uses the things that we've already done in the class. Okay? So first, I'll call this proof 1. This is the one that assumes a modicum of group theory. So here's what we'll do. There is a group here, actually, called Z mod NZ star. This is the set of numbers modulo n that are coprime to n, or equivalence classes of such things. So I'll write that very explicitly. Square brackets 1, well, dot 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 up to, I'll just write this as square brackets, b, so the equivalence class of numbers mod n. I don't know, I guess I already introduced this. I'll just write it as that. A, or b, such that 1 is less than or equal to b, is less than or equal to n, and the GCD of b and n is equal to 1, is a group under multiplication and reduction modulo n. Under multiplication and reduction mod n. So what I mean by that is you take 2 numbers, you multiply them in the usual way, you take the remainder upon division by n, and that's the result. So for example, if you multiply 3 times 7, here you get 21, the remainder upon division by 10 is 1, so 3 times 7 is equal to 1 in the group Z mod 10 Z star. So that's the multiplicative group of integers modulo n. And A, you can view it as an element of that group. And there's a fact in group theory, which is that the order of an element of a group divides the order of the group. So the order of an element of a group divides the order of the group. Element of a group divides the cardinality or order, cardinality, which in this case is the cardinality of Z mod n Z star, which happens to be exactly what I just defined Phi of N to be, of the group. Now there are a few problems with this if you don't know group theory. Namely, you have no idea what I mean by the order of an element. So if you don't know group theory or algebra, then the circled blue statement should mean absolutely nothing to you. And then second, even if you did know what that means, you don't know a proof of this statement. And so it should be very unsatisfactory to you if you don't know algebra, abstract algebra. So let me just tell you quickly what the blue circle thing means, and then give a completely different proof of this that allows you to not have to worry about this. But if you do know group theory, then this is nice. And when you do take group theory, you'll prove this in some abstract way in a general group, and you'll go, oh, it's just a special, that's just a generalization of what I already saw how to prove here, which will make group theory easier. Okay, so the order of an element, that's the following. Definition, the order of A mod n is the smallest power of A that equals 1 mod n. Where when I say smallest, I mean greater than or equal to 1. So what you do is you consider A to the power of 1 mod n, you consider A to the power of 2 mod n, etc. And at some point, hopefully, you eventually get a to the power of k equal to 1 mod n. The smallest k for which this works is the order. There's an annoying thing about this definition, though. What if there is no such k? How do you know? Like, you just take some random element, mod n, and then start raising it to powers. Who's to say that you're ever going to see that one of those powers is congruent to one of all things modulo n? So it takes a little argument to see that that actually happens. Of course, once you knew this theorem, you would know that phi of n in fact works, and so at least something, at least the order is defined, and it would be a divisor of phi of n. So that's the definition of order, it's just the smallest thing. So if the order of an element divides the order of the group, then that tells you that k, the order of the element, divides phi of n. So a to the power of some divisor of phi of n is 1, and hence a to the power of phi of n is 1 as well. So that's the group theory argument. Now let me just give you a completely straightforward elementary argument using things that you already know about for the same statement. So I'll call that proof 2. Okay? So I'm going to try to convince you that if you take a and raise it to the power of phi of n, you'll get 1. Without using any hocus pocus from another course that you haven't taken yet. So here's the idea. I hope you remember the notion of a complete set of residues modulo n. So we'll do something kind of like that. What we're going to do is take these numbers mod n, the elements of z mod n z star, and just multiply them all together. And then what we'll do is we'll take them and multiply them all by a, and multiply all of those together. And the two things we're using are basically the same, so they'll have to be congruent modulo n. It's just that the order in which we're doing the multiplication is different. And then you just cancel from both sides, and you arrive at exactly that conclusion. Okay, so let me just write this down. So consider the product of b, where b runs through these numbers modulo n that are co-primed to n. So here b runs through z mod and z star. Just take all these numbers and multiply them all together. Okay, that's a product. It's just some number modulo n. When I say this, I mean you're multiplying them all together and reducing modulo n. I don't care too much what the result is for this argument. We will in a minute when we look at Wilson's theorem. But another thing you can do is take these numbers and multiply them all by a. So consider a times b, where you take the product over all b and z mod and z star. And so what happens here, if you take all of the numbers in this set and multiply them all by a, you're getting a bunch more numbers that are also co-prime to n. And moreover, you're not going to have a situation where a times b is congruent to a times b prime mod n without b being equal to b prime, which I think Simon must have proved this, but the proof is just if you subtract on both sides, you'd have to have this as 0 mod n, but nothing on the a has nothing to do with n, so b has to equal b prime. Like that, b minus b prime has to be divisible by n, because n and a are co-prime. So the prime factors are completely different. Okay, so that gives you that b is equal to b prime. So if you take the set of numbers here and then multiply them all by a, you get an injective map from this finite set into itself. So this is the map b goes to b times a. And so you get exactly the same collection of numbers, because an injective, an inclusion from a finite set into itself, has to be a bijection. It has to be 1 to 1 and onto. So these two sets are equal, or rather these two products are equal. But if you just rewrite this product on the right-hand side a little bit, it's the product, well, it's a to the power of phi of n times the product of all these b's, b and z mod and z star. Okay, and now you can just cancel that product of b on both sides, and out pops the theorem that I claimed, right? This is a number that's coprime to n, since it's a product of numbers coprime to n, as is that, and so we end up with this number coprime to n equals something a to the power of phi of n times that same number. So we just cancel both sides, boom, and we get that 1 is equal to a to the power of phi of n, always working modulo n. So the congruence in there. Okay, so that proves this statement. Any questions? Okay, so that's Euler's theorem. Fermat's little theorem is just exactly the statement in the special case when n is a prime number. It says that if n is prime, a to the power of p minus 1 is congruent to 1 mod p. By the way, this is a really powerful primality test. If you take a big number and you think it's prime, all you have to do is just take some random a and compute, say 2 to the power of p minus 1. If that's not 1 mod p, then you know instantly that your big number is actually not prime. That doesn't always work to tell you whether or not a number is prime, but it'll often tell you with high probability that a number isn't prime. And when you do that, it tells you with absolute certainty the number is not prime. Okay, so that's this. So Fermat is just the case n equals a prime. All right, next, Wilson's theorem. You might think of this as the worst primality test of all time, and it's the following theorem. P minus 1 factorial is congruent to minus 1 mod p if and only if p is prime. So if you want to know whether some huge number is prime, all you do is compute p minus 1 factorial divided by p and see if you get a remainder of minus 1. Easy peasy. But actually, that would be really, really hard to do. But let's prove it. So this will be the proof of Wilson's theorem. And so what we're going to do is just consider, so there's two directions. I might have time to only do one. But let's assume that p is prime. So assume p prime. It's an infinitely of statement, so you have to assume each direction and then prove the other one. So assuming p is prime, let's compute p minus 1 factorial. Okay, so let's assume p is prime. And we're interested in what p minus 1 factorial is. Well, p minus 1 factorial is 1 times 2 times 3, all the way up through p minus 1. I want to know what it is modulo p. So every single one of these numbers is co-prime to the prime p, because we're assuming p is prime. So these are each co-prime to p. And what I'm going to do is just pair them off. If you take a number here like 2, there's some number in here such that 2 times it is congruent to 1 mod p. Because, so 2 times x congruent to 1 mod p, this is a linear equation, mod p, and because 2 is co-prime to p, it has a solution. And again, I believe that you guys saw that using the extended Euclidean algorithm. You write 2 and p, you find an a and a b, so that 2 times a plus p times b is equal to 1, and then using that you can read off an x that solves this equation. Or you can use a complete set of residues, you multiply and you find the same set again, and therefore there has to be a solution. So that should have been proved in the book. It is in the book and should have been proved by somebody. So for every single number here, say 2, there's another number here so that the product is 1. If that worked in such a way that for each number the other one was a different one, you could just pair them all off in pairs, and then when you multiply them all together, you'd end up with 1, because you'd always have the thing in its inverse. So that better not work for every single one. But it works for most of them. Let's see for which one it might not work. All right, so imagine you have a number, one of these numbers from 1 up to p minus 1, with the property that its inverse, that is the solution to that number times x equals 1 mod p, is the same number again. So suppose you have a number so that a times a is 1 mod p. What can you conclude about a? Well, it says that a squared is 1 mod p. And that means that p divides a minus 1 times a plus 1. I just subtracted 1 from both sides, factored it, and then used the definition of congruence. P is a prime, so if p divides a minus 1 times a plus 1, p divides one or the other, which means that either a is 1 or a is minus 1, mod p. So these two are the annoying ones with the property that they don't pair off with a different inverse. But all the other ones, from 2 up to p minus 2, do. So when you multiply these together, every single one you always have an inverse, so you always get 1. And all you're left with is 1 times p minus 1, so this whole product is p minus 1, which is just minus 1 mod p. Done. And the other direction is actually a lot easier, and I'll leave it to you to read that though. Alright, we'll start with the Chinese remainder theorem on Monday. Or on the next day, which is Friday. Sorry.
Okay, so the homework that's good
Yeah.
stuff on the calculating the first two digits.
Hints. Use floating point numbers. Instead of, you don't do anything with modular arithmetic. If you use floating point numbers, like on your calculator, like in a numerical analysis class. It's like the other side. Numbers mod n, numbers mod 10 and mod powers of 10, they give you the last few digits. Floating point numbers that they use in engineering, like 2.7 floating point numbers, to some fixed precision, they give you the first few digits. So you can think about how you work with maybe scientific notation and fixed but small precision floating point numbers. And say you enter them in a decimal. Nope, there's no, so mod is, all of modular arithmetic is about like that side of the number, the last few digits. And then there's one other, there's one other way to look, so
Yeah, I know. It sounds
in
like
terms of completions of the rational numbers, there's like all these periodic
my
numbers,
phi
all the primes, where you see mod primes. And then there's one other thing which is the normal absolute value, where you have the real numbers. So basically the trick to this one is just to use real numbers, which are,
I don't understand why that's
they're really good at giving you the first few digits of a number rather than the last few.
product B.
If you just imagine, say you have two numbers and you want to compute the first few digits of their product, you could just write them in scientific notation, multiply literally the first few digits,
Yeah.
keeping track of the exponent, and you get the first few digits of the product.
Except it's in percent, which means it's just the power of something consistent with large.
Doesn't matter. It works in exactly the same way. Think about it in scientific notation, and then large doesn't. You just need information about the first few digits. Let me stop this thing.
It's a question about like why the phi pk equal to pk minus 1.